The second video of changes of concentration with time for rate laws is the second order rate law. And so in this one, you can have either A and B be to 1, or you can have A being squared. And so these equations are given to you, but I don't identify what equation is what. In other words, I will give you the previous equation. I'll give you this equation, but I don't tell you that it's first order. I give you this equation, but I don't tell you that it's second order. So you have to know which equation is which. So again, it's 1 over the concentration at time t is K, which is the rate constant, times T, which is time, plus 1 over the initial concentration. So a problem like this says that iodine atoms combine to form molecular iodine gas in the gas phase, and it shows the reaction. The reaction follows a second order kinetics. So again, it will tell you in the problem what order it is. It has a rate constant, which we know is now K, of 7.0 times 10 to the 9th molar, per molar second. Temperature, again, given because of the fact that the rate constant is temperature dependent, but we're not going to use it. And it tells me that the initial concentration of I was 0.086 molar. And they want to know what the concentration is at 2.0 minutes. And this is 0, is what they want to know. And of course, my time then is 2.0 minutes. Now again, before I start, you'll notice that this is in seconds, this is in minutes, so I need to multiply by 60 to give me 120 seconds. Okay, the equation is 1 over the concentration of I at 2.0 is KT plus 1 over the concentration of I initially. So it's going to be 7.0 times 10 to the 9th times 120 plus 1 over 0.086 . I multiply these two things together, I get 8.4 times 10 to the 11th. I take the inverse here and I get 11.6. Now this is such a large number it doesn't change it, so it basically stays 8.4 times 10 to the 11th. And this is all 1 over the concentration of I. And so I is 1 divided by 8.4 times 10 to the 11th. And so it's going to give me a very tiny number of 1.19 times 10 to the minus 12th molar. Okay, so that's how you do a second order kinetics. The next one, the last one, is a zero order kinetics. So we have, and this one was introduced later in the textbook versions, so therefore that's why it's after. Okay, so it was first order, second order, and then zero order. So basically it's saying that the concentration has no effect on the rate reaction, so it's A to the 0, or rate is just equal to the rate constant. And that equation is the concentration at time t is equal to a negative kT plus the concentration, the initial concentration. So here's a problem with this. Again, this is a zero order. It will always tell you in the problem. And they want to know what is the concentration of A after 2.0 minutes. If my initial concentration of A is 3.4 times 10 to the negative 1 molar. The rate constant, so K, is 1.37 times 10 to the minus 3 molar per second. And again, my temperature is given because of the fact that K is temperature dependent. Okay, so the equation was A at 2.0 is equal to a negative KT plus, this one's T, plus the A initially. Okay, again, this is seconds, okay? I didn't write down the fact that time. It told me the time was 2.0 minutes. But seconds, minutes, so I have to multiply by 60 to get 120 seconds. Okay, so my concentration at 2.0 is a negative 1.37 times 10 to the minus 3 times 120 plus the 3.4 times 10 to negative 1. I multiply these two together, I get a negative 0.1644 plus the 3.4 times 10 to negative 1. So when I add those together, I get 0.176 molar. Okay, so for any reactant, it should decrease in concentration as time goes on. This is basically the same thing as saying 0.34, and so in fact that is in fact less. Okay, and so that is how you do a second order and a zero order integrated rate law.